Hello everyone, good afternoon. Welcome to our Tech Talk speaker series, the first session after a long break. I'm really delighted to introduce Jobayer Hossain, one of our own ACCEL CTR biostatistician from Nemours, a long-time and very active member of the ACCEL CTR Biostatistic Epidemiology Research Design Core, or BIRD. And so Jobayer is our speaker today. But before I introduce him, let me mention some housekeeping issues. As always, we will continue to provide CME credits for our Tech Talks and our ID series presentations. We will distribute the information via email to those that registered for today's event. If you did not register prior to today's talk, you can still obtain CME code information from Lisa Maturo, and I will write her email address in the chat box. Our June 11th ID series, so it's next week in the ID series on Friday. Do not miss Dr. Theodore Corbin from Drexel University, who will talk about Through the Lens of Trauma, Approach to Stress, Violence, and Adversity. And then our next Tech Talk, so we have Tech Talks every month, will be Dr. Bethany Wolf from MUSC, and we will provide her title later. So again, I'm really delighted to introduce Dr. Jobayer Hossain. Dr. Hossain has multiple titles. He is the director of the Nemours Biostatistic Program at Nemours Children's Health System, as well as a senior research scientist in the biomedical research at Nemours Children's Health System. He is also an adjunct associate professor in the Department of Applied Economics and Statistics at University of Delaware. He obtained a PhD in statistics from Southern Methodist University in Dallas, Texas, and began his career in statistics by being the assistant director of the Central Bank in Bangladesh. He has more than 100 publications. He was PI of the Cobre Pilot grant and has been co-investigator in multiple federal and foundation grants. And is also, as I mentioned earlier, a very active member of our CTR BIRD group. So thank you so much, Jobayer, and we look forward to hearing your presentation.
Thank you so much, Claudine, and welcome to all of you in this presentation of post-hoc mixed models of the best linear unbiased predictors from linear mixed effects models, an approach for clustering unbalanced longitudinal data with irregularly spaced intervals. Presentation outline. At the very beginning, a brief background and motivation of this longitudinal data clustering, and then it will cover a little bit of longitudinal with irregularly spaced intervals, about homogeneous linear mixed effects model, as well as mixer-based mixed effects model. Then the one we are talking about post-hoc mixer modeling of the best linear unbiased predictors from mixed effects model. It will be followed by the classification comparison between and evaluation also, between three methods, and then also there will be external validation using the simulation, and at last the conclusion. Classification of longitudinal trajectories is a topic of growing interest. Necessarily occurring data, such as electronic medical records, have shown great utility in learning healthcare systems and personalized medical decisions. Observation times in these data are often irregularly spaced intervals and vary across individuals. Repeated measures of this type are usually expressed as a function of time and are described by the level and shapes of the curve. Linear mixed effects regression model this data as a combination of average population, temporal trend, and subject-specific effects. Typical approaches for clustering longitudinal data with fixed time may not be suitable for clustering this data. Mixer-based mixed-effects models are mainly used for the classification of this data. In the general form of the linear mixed effects model, BI, the vector of random coefficients, describes how the trend over time for the ith individual deviate from the population trend. BI is a random effects, and the assumption is it is multivariate normal with mean 0 and a covariance matrix, like kind of homogeneous covariance matrix. Beta is a vector of fixed effects, we know, and that is beta describes the average population trend. Whereas BI is the most important one. BI actually accounts for individual level trajectories, heterogeneity in the individual level trajectories. Well, with this setup, the data is also a multivariate normal, and here is the with mean xi beta, and here is the mean variance the covariance matrix. We define that as BI. Under the above distribution of BI, the model is known as homogeneous linear mixed effects model. Under the homogeneity, the empirical BLUP, the BLUP, like the basically unbiased predictor of individual level trajectories or individual level heterogeneity in the individual level trajectories, can be expressed as like conditional expectation of the BI for given data of the ith subject. And as BI and YI both are multivariate normal, we know by the rule, this is a basically unbiased predictor actually by the conditional aspect. That is the rule actually, and we know the expression we have here, that is covariance D and G are the covariance between BI and YI. BI is the variance matrix of the YI, and then and we know that this is a function of YI minus expectation of YI, and that is the expectation of YI is the xi minus beta. So this is commonly developed from the regular conditional expectations theorem. So we learned about the homogeneity, and we know how to extract the best linear unbiased predictor of heterogeneity in trajectories actually. But in violation of homogeneity assumption, Barbeck et al. Actually suggested a Gaussian mixed distribution of BI, that is a weighted distribution of multivariate normal, weighted sum of multivariate normal with a component specific mean and a common covariance matrix. Phi j is the component probability or mixing proportion. And this is actually known as heterogeneity. The BI under the heterogeneous trajectories, and the assumption, and YI is still the data. YI is the data, and that is still multivariate normal with this expression. And then empirical BLUP under this heterogeneity assumption is like empirical BLUP under the homogeneity model plus a correction factor, that where AI is this and pi is the posterior probability of being in the ith subject in the Z group, and mu is G is the component mean. The model, as I said, like the model is known as heterogeneous mixed effects model, and it was first included in SAS macro and was found computationally expensive. HLME et al. Extended this model to which both fixed and random effects means which both mean and variance or covariance matrix as a component specific, and then they implemented this in R package LCMM. Following Babak et al., Mithun et al. Introduced a similar method that also combined multi-level mixed effects model. I mean, the same thing, like what we say mixed effects model or hierarchical mixed effects model, whatever it is. This is the same concept. And then they use also the combination of the mixed effects and mixed models. They implemented the same things in the software of Mplus. The method gained as popularity as a growth mixer model. Both the method, like the one we say are heterogeneous linear mixed effects model and Mplus GMM, built on the same concept of combination of mixed effects and mixer models. Both methods are inherent some limitations, especially computationally. Sometimes it's very expensive and complex. Compression time increases with the increase in time, increase in sample size, degree of unbalancedness, complexity of the parametric curve, and number of random effects. In LCMM, HLME, the program may not converge, but may reach the maximum number of iterations fixed at 100 in some cases. GMM programming seems to be developed assuming limited number of observations per subject with the same measurement time across individuals. Observations are usually thinned and aligned to nearest time points. As we have in example, we needed to thin and we needed to align the time points of measurement to a common nearest time points. Posthoc mixer model assumes a Gaussian application of Gaussian mixer model to the empirical BLUP of BI that is estimated or predicted under homogeneity assumption of the model. We know, like under the homogeneous assumption, the model BI is multivariate normal with mean 0 and the covariance matrix of D. But still, it accounts for all kinds of heterogeneity. And the thing is that although we have in the model beta that is fixed, and we can count as a threshold, and BI is the heterogeneity and deviating from the threshold. So BI is accounting basically all kinds of heterogeneity available in the data. In presence of G mixer components, Gaussian mixer actually assumes each component to be multivariate normal. That is, the coefficients for ith subject and the conditioning of belongs to the group G or K actually is distributed with mean mu K and the covariance matrix GK. Marginal distribution of BI, that is the important thing for us, and that is a weighted mean of the weighted multivariate normal mu K dk and weighted sum actually, weighted sum of the multiplicity, normal, mu k, dk, and weights are the component probability. And the likelihood function of theta, and when we condition B1, B condition, if we condition the prediction of B1, B2, and Bn means the like regression coefficients for the random coefficients for each subject, and if we condition that on the BLUP, this likelihood function becomes the function of only phi k, mu k, and dk, and all those are for the each of the components, k component. And once we condition that, actually this becomes the regular Gaussian mixture model, and BI estimate is kind of data for the analysis. As multivariate normal, components are ellipsoids centered at the mean vector mu k, and with geometric features such as volume, shape, and orientation, determined by the eigenvalue decomposition of the covariance matrix, component-specific covariance matrix, where lambda k is a scalar and that controls the volume. The CK is a diagonal matrix, specifies the shape of the ellipsoids, and AK is an orthogonal matrix that determines the location of the ellipsoids in the multivariate regions, and I mean like that is the orientation. The parameters lambda k, AK, and CK can be constrained to be equal or variable across groups. On considering and combination of permuting them, we have actually there are total 14 potential models. Steps involving the post-hoc mixture modeling of BLUPS from mixed mix model. We need to fit a linear or piecewise linear mixed mix model under the assumption of homogeneity. Why we are considering only linear or piecewise linear? Like when a function is the most simple when it is linear, because you are expressing the function by its slope and intercept. And then we extract the empirical BLUPS, apply a Gaussian mixture model to classify BLUPS. Then we select a few cluster solution using inbuilt post-fit statistics. We have actually BIC, and we have a lot of suggestions for the many model we can choose based on the BIC, and then we can use. That means in the Gaussian mixture model we choose multiple solution, and then for each solution we fit a model in the basic model. In the step 1, we add a classification identifier and in its interaction with time. Then we compare the goodness of fit statistics such as AIC or BIC to select optimum classification, and we term it as a mixed model based evaluation. Then for the application, we used 5 data sets of early childhood growth patterns, and we use these for comparing the performance of classification and also for the evaluation. Each dataset actually contains 2 to 3 subsets of plausibly homogeneous growth patterns of linear or quadratic or cubic trends. We have identified these trends actually from a large dataset of 3365 children. data were collected on children clinic visits during the first 5 years of life, and then it was retrieved later for the analysis. We calculate weight per length for the age group less than 2 years and body mass index for greater than 2 years, and we use the standardized scores of these two variables as the growth indicator and fitted a basic model of the following one, the piecewise linear mixed sequence model, where B1, B2, and B3, we have actually two nodes. Maybe at different for different data set, different time points. We generated classifications of 2 to 5 groups using the 4 methods. One is mixer-based mixed effects model from using the Mplus. Then we also use mixer-based mixed effects model in our RHLME package. And then Gaussian mixer model of BLUPS, as well as Gaussian mixer model of principal component of BLUPS. Using principal component of BLUPS actually help us to avoid using some of the outlier. And there are two kinds of evaluation we did. One is internal evaluation and one is external evaluation. So for the internal evaluation, we used post-peak statistics. For the GMM, mixer-based mixed effects GMM, we used their inbuilt Mplus evaluation as well as mixed model evaluation. And for the HLME, means heterogeneous linear mixed effects model in our package LCMM, we use their evaluation as well as mixed model evaluation. And then mixed model for classification of evaluation was this actually. That's what we said in the last slides. The very first data set is a 3-component. And as I said, like that, it was artificially formed. We identified actually 3 components from a large data set, and we used them forming a data set of 3 components, 3 plausible components. And we see that the first one might be a linear, then it is a little concave down, or this may be a concave up, something like that. So we know that this is a kind of distinct 3 components, and we wanted to see how 3 methods classify this data set. We used, as we know, 3 data set, 3 components, and if we look at the first 3 components, we see all methods did a very good job in classifying in the 3 components into 3 groups. As well as in the evaluation, Mplus evaluation also picked 3 group classification as the best, and then LCMM also picked as the 3 group, as well as mixed effects model evaluation also picked the 3 group classification as the best solution for this classification of this data set. But if you look at if we compress without knowing, actually, if we'd like to compress how different 3 groups, how the methods do the classification. If we look at the 2 groups, we see that GMM means Mplus classification, and like the BLUP, and BLUP LNT means the principal component of the BLUP, Posthoc mixer model BLUP, and principal component of the BLUP actually combined component 1 and 3 while HLME splits all of them. And we have we also wanted to see how they classify if we make more classification rather than just getting 3 components or 3 groups. Like how does it 4 and 5? It seems that GMM has a little similarity with the BLUP and then HLME on this dataset. But next dataset is actually again 3 component, and this one is less distinct because you see like that component 2 and component 3 may have some kind of overlapping. And in 3 group classification, we see that GMM in Mplus did still very good, and HLME also did good. All methods again did a very good job. But when we merged when we wanted to compress into classification, we see that GMM actually combined component 1 and component 3, and component 1 and component 2, and the HLME component 1 and component 3, and the 2 other methods, actually BLUP methods, they combine component 2 and 3. But basically, in the evaluation, if you look at the Mplus evaluation, they pick the higher the number of classification, they pick the better as a solution. That might not be a very good situation for classification. Whereas we see in the same evaluation, if we did mixed prefix model, then it picked the 3 group as a best for this, and for BLUP and T, they picked as a 2 group with combining this component 2 and component 3 as the best. But we see that HLME, BLUP, and BLUP LNT actually they are the same evaluation because they have the same 3 group evaluation, and they have the same classification for the 3 groups. The next one is also a 3 group, and again it is a less separable, and we see like the classifications kind of in each method differed or varied between methods. And actually we have still the second for the 3 group, we have BLUP and BLUP LNT have identified second and third as the same and merged a few from the one with the second. And whereas in the GMM, they did first and second as a separate, and then they split third. Now, first and second in one group, and they split the third as the 2 group. And here, when we look at the evaluation, we found, using the mixed effects model evaluation, we found that the BLUP and BLUP LNT 3 group solution is the best solution based on the mixed effect model fitting. This is a 2 group and a very distinct 2 group. One is concave down and another is concave up components. And we see that GMM, BLUP, and BLUP LNT means principal component based classification of post-hoc model. They did completely separated like the two components completely, 50 and 83 in both group. In all three methods did a very good job in identifying these two distinct groups, whereas in HLME it did a clustering classification, like they just split two groups, and you can see at the below like two groups is like contains, each of the group actually contains heterogeneous trajectories. That doesn't make sense much. And in the third group also, like the if we consider making more groups, then we see that component like GMM, and the first one actually, like the component 1 is distinct in each method, and all methods actually separated second component, and in the GMM only 4 was separated, whereas in the HLME 11 of them separated, and in the BLUP and BLUP LNT actually almost half and half. And we see here, if we all method actually except the HLME, because their two group is not good, but the mixed prefix model actually identified the group, like the two group classification as the best, whereas Mplus and RHLME both actually went for the 4 classification, and 4 classification is like still the the first component is intact in all methods, and they actually separated like only the group component 2 trajectories. So here we see that it does not make sense, the classification, two group classification using the HLME. The next one is also like the second one is also two group plausibly, but I mean here HLME, the GMM and BLUP and BLUP LNT actually identified two group is almost as to the two components as a two group, except one or two trajectories actually exchange their component groups, whereas in HLME they merge both component, only 4 they put as other group, and all other actually they put in one group. That does not actually even look like the things same, because they are actually even every strand is different. And in the evaluation, Mplus actually identified also two group as the best. GMM also identified as the two group as the best, and in the GMM group classifications, and using BLUP and BLUP LNT, we have actually minimum classification 46 minimum among 4 groups BIC, but GMM actually also suggests like another one, like the 4 group classification as the best classification for with the minimum BIC of the mixed prefix model. So that was the internal validation. Then we thought, okay, we need to see how this data, if we generate used to this data and these classifications, and if we generate like many data sets, and if then we wanted to see how the simulated data agrees with the how the classifications of simulated data and real data means, I mean, like the similarity between the classifications of simulated and real data. So we used like each classification for each data set, and we used our package POX to simulate the data. And also we use that each data and each method of classification we used for simulating 200 data sets. And then we did the classification of all of them using the corresponding method. And then we used 6 classification evolution indices. And at last we averages for of the evolution indices for 200 simulations to see the average agreement between the classifications of real and simulated data. For the classification indices, we used the 6 of them. Like the first one was proportion agreement index, and variation information, RAND index, Mirkin index, and Polkis and Mallows index. Among these 6 indexes, like the proportion agreement index and RAND index, adjusted RAND index, and Polkis and Mallows index, actually lies between 1, and it will be 1 when there is a complete agreement between 2 classification vectors. When 2 classification vectors exactly matches with each other. Whereas like the Mirkin index and variation information, that the minimum value is 0, and that 0 is when the 2 classifications exactly matches. So in the very first data set, think about the data set 1, we saw that all 3 methods did a very good job in classification and evaluation. All of them 3 identified as a 3-group classification as the best. Here we see actually 4 methods, and you see like the mean agreement proportion and R means RAND index, adjusted RAND index, and Polkis index. These are the highest. One means there is a very good agreement between the classifications of real and simulated data. And whereas variation information and the Mirkin index actually needs to be close to 0 or close to 0 to identify or to say the classification is the good or acceptable agreement between simulated and real data classifications. If you see like the Posthoc and HLME and Mplus, you see the best method, the Posthoc, like for the almost 1, the 1 needs to be close to 1. All 4 of them is close to 1. And the mean variation information, that is even close to 0. And the mean Mirkin index is high. And it's actually geometrically, it gets very high even with a small variation. So if you look at the next one, HLME, that's also very high, 0.9x, close to 1, and then RAND index is close to 1, and AR is close to 0.91 or 92, and these are all acceptable agreement. And but if you look at the highest agreement shows Posthoc mixer modeling and classification. And then it is followed by the HLME as well as the last, like the Mplus. And Mplus did a little, even Mplus classification or agreement is not highly acceptable. It would be kind of marginally acceptable. It is 0.88, then 0.85, 0.71 is the adjusted RAND index. That is one of the most important one. And then Polkis index is 0.88. And it's much smaller than Posthoc and HLME. And the second data set also like that, we see Posthoc mixed model did a pretty good job, except Mirkin index, a little high value. And as I said, like the even with a smaller difference between the classification vectors, even we can end up with a very large number. So other than that, all other methods shows a very high agreement between real classifications of real and simulated data sets in Posthoc and HLME, as well as actually Mplus also did very good job on this one. The next one is also that one was done was not very good for not very separable, but it's still Posthoc and HLME had a good classification agreement. Doesn't matter whatever they classified the structure they extracted from the real data, they continue the same thing in the simulated data. And Mplus actually did worse in this and not very acceptable. We don't see very acceptable agreement between the classifications of real and EA data, simulated data. We remember this one is just two components, and it has like the very distinct two components. And we see that it is exactly almost one, in the mean agreement, and all of the the RAN index, adjusted RAN index, and Polk's index, all of them shows almost one in the Posthoc. HLME did worse in the classification, as well as it did worse in the this simulation evaluation, but Mplus did a very great job and shows a very good agreement between classification of structure of in the real data and the simulated data. The next one is also the Posthoc mixer model did very good job in showing the great agreement between Posthoc between real and simulated data structure classification, and whereas HLME and Mplus is not very good in extracting or showing the agreement between real and simulated data. So we talk about the three methods. We saw the internal validation of the data, and also we saw that simulation-based external validation. And now, definitely we are going for the conclusion. In conclusions, classification performance largely depends on the accuracy of the model fit in all methods, so that we can actually account for the heterogeneity, we can have the random effects to account for the heterogeneity well in the dataset. Then, for dataset with clearly separable components, methods perform an acceptable level of accuracy for classification as well as evaluation. That's what we saw in very first dataset. All methods did the same thing. And methods differ in performance dataset with less separability of the subgroups. Even Posthoc mixer modeling of BLUPS perform much better than two other methods in this situation. In simulation studies, for all datasets, we have 5 datasets, and then we saw that Posthoc mixer modeling shows greatest level of agreement between classifications of real and simulated datasets, and also shows the best consistency across 200 simulated datasets. Unlike HLME, means heterogeneous linear mixed reverse model in LCMM and GMM in Mplus, Posthoc mixer modeling of BLUPS can be implemented in most mainstream statistical software. And it does not impose serious computational burden for the increase in size of the dataset and extent of the unbalancedness of the or imbalancedness of the dataset. And it is also less likely to be affected by the problem related to multiple maxima of the likelihood function or log likelihood function. Future studies could further insight in these three methods classification performance. Benjamin A. Levy, the head of the biostatistics at Thomas Jefferson, he is also worked with me on this with me, and he helped me GMM for the analysis of GMM in Mplus. Thank you so much for being in this presentation, and please let me know that any questions or concerns, whatever you have.
Thank you so much, Jobayer. This was really a very stimulating and interesting presentation. Any question for Jobayer? Keshab, do you have a question?
So, Jobayer, when we identify these groups, how would we, characterize these groups? Are we just going to say we identified these three groups as the optimal number of groups and just leave there, or how would we characterize this group?
In the classification, the main problem is grouping, optimally grouping. And you know that optimal group actually depends on how the data are or how the components are there, plausible components. So when you classify the components and when you have optimal grouping, of course you can characterize them as you can characterize as a subgroup. For each of the group, you can characterize like the demographic or any other clinical purpose or anything you want. You can classify or you can characterize this by groups. Or if you want to account for anything, even you can add a variable in the model, and that will account for that. But I would prefer class classification and then for characterization of the groups, features.
Thank you.
Any other questions? So I have a quick question, Jobayer. So I think you convinced us that the post-hoc mixture modeling was the best ever. So in which are there circumstances where you would use the other types of models rather than the post-hoc mixture, BLUP? Or you think we should always, now that you've demonstrated that it worked really well, we should always use the post-hoc?
Yeah, all I want to say, the GMM is and like the HLME are two established method. Mainly, the GMM is applied frequently in, especially in psychological and psychometry. People often use, but the problem of the GMM, it does very good job actually in classification, but only it is not very useful for the large data set, and also it is we need to thin and we need to align the data to a nearest time points to make it as a fixed time points. On the other hand, HLME can handle the large data set, but not very consistent. I did not find at least consistent. By the by, we use the same model, piecewise mixed reports model, in all three methods. And these are all methods are mixer-based mixed reports model. But the thing is that for the computational problem might be, it is the LCMM I did not find. In fact, I wrote the Proust lemma also, that about this two group classification, why it's so weird. She wanted me to send everything, but actually, and also to go some link to talk about more about this problem, so that other people also can try to see if there is a problem. But I did not find a very good solution, because it should not do anything, because this is the model fit, and then based on the model fit, you will get the data, classification. But it was not very perfect, but we saw that some of the other classifications did a very good job using the same model. So, I mean, all I want to say, although under the homogeneity assumptions, like it is that we can account, the empirical BLUPs can account for, as long as the model is good, empirical BLUPs can account the heterogeneity in the dataset, and it is still can be applied. There is no intention to show that it is better than these two methods, but the intention is it can be a parallel method.
Thank you. I think it's very useful for all of us who work with electronic health records, where the intervals between time points is extremely variable for each patient. So I'm sure we'll find really good applications for this model. Any other questions? All right. Well, thank you so much, Jobayer, for this really very clear and wonderful presentation. And thank you everyone for attending our seminar. And we'll see you next week.
Thank you.
Thank you. Bye.